Have you ever stopped to wonder what computer science actually is? We're going to find out today by taking a pretty wild journey. We're going to build our entire digital world from the ground up, starting with just a single idea.
So let's ask it straight up. What is computer science? A lot of people think it's just about coding, learning Python or C++, but that's not really it. That's just one piece of the puzzle. The real thing is so much deeper, and honestly, way cooler. To really get it, we're going to follow the ultimate blueprint. We're going to construct the entire field, from its absolute foundation all the way up to the internet that connects every single one of us. This is basically the architectural plan for our modern age.
So, where does a journey like this even begin? Well, it's not with silicone chips or fancy lines of code. Nope. It starts right here, in the world of pure thought, with logic and with math. This is the language that everything else is built on. It all boils down to this one, incredibly simple, yet totally world-changing idea from something called propositional logic. Get this, every single statement has to be either true or false. That's it. No maybes, no sort of, no in between. And that simple binary choice, well, that's the single atom that the entire digital universe is going to be built from. Now, to actually work with these ideas, you need the right tools, right? And for computer scientists, that toolkit is math. Discrete math gives us the hard and fast rules of logic. Linear algebra is the powerhouse behind graphics and data. Probability lets us make sense of uncertainty, and calculus helps us understand how things change. These are the instruments we're going to use to compose our digital symphony.
Okay, but pure logic is just an idea. You can't hold it in your hand. How do we make it actually do something in the real world? This next layer of our blueprint is where we bridge that gap between the abstract and the physical. It's time to build a machine. And this is where the real magic happens. We take those abstract ideas of true and false, and we just give them new names, 1 and 0. Then, and this is the genius part, we represent those numbers with a tiny physical switch called a transistor. It can be on, representing a 1, or off, representing a 0. You see where this is going? By combining these simple switches, we can create what are called logic gates, the tiny little decision makers of our computer. Check this out. This is an AND gate. It's super simple. It only outputs a 1, which means true if input A and input B are both 1. That's the whole rule. It's just a tiny, predictable little thing. But what if you combine thousands, millions, even billions of these simple little gates? Well, just like Lego bricks, you can build something incredibly complex and powerful. And what exactly do we build with all those Lego bricks? We build this, the brain of the computer, the Central Processing Unit, or CPU. This is where pretty much all the thinking actually happens. Now, if you could peek inside that brain, you'd see it has two main parts doing most of the work. First, you've got the calculator, the arithmetic logic unit, or ALU. It's the number cruncher. It does all the math and all the logical comparisons. Then you have the traffic cop, which we call the control unit, or CU. It's in charge of everything, directing the flow of data and telling all the other parts what to do and when to do it.
So how does this brain actually run a program? It's through this relentless, ridiculously fast cycle. It fetches an instruction from memory, it decodes that instruction to figure out what it's supposed to do, and then it executes it. Fetch, decode, execute. Over and over, billions of times every single second. This is the very heartbeat that brings the whole machine to life.
All right, so we've built the hardware brain, but a brain with no thoughts is kind of useless, right? It's just a chunk of silicon. That brings us to our next layer, the software, the stuff that actually tells the hardware what to do.
And the most important piece of software, the boss of all the other software, is the operating system, or OS. The best way to think about it is like the conductor of a huge orchestra. It manages the CPU, the memory, the storage, all the different hardware musicians, and it makes sure they all play together perfectly so that your apps, your browser, your games can run without a hitch. So how does software actually solve problems? Through things called algorithms. Now, don't let the fancy words scare you. An algorithm is nothing more than a step-by-step recipe. Seriously, if you're sorting a list of names or trying to find the fastest way to drive to a friend's house, the algorithm is just the set of instructions that tells the computer exactly how to get it done. And just like in a real kitchen, there's more than one way to write a recipe. You've got different strategies. Divide and conquer is all about breaking a massive problem down into little bite-sized pieces. A greedy algorithm just makes the best choice it can see right now and hopes for the best. And dynamic programming is the smart, efficient one. It remembers its past work so it doesn't have to solve the same problem twice. It's all about finding the cleverest recipe for the job.
So, how do we give these recipes to the computer? I mean, we know it only understands ones and zeros. Well, that's what programming languages are for. Languages like C are the bridge. They let us humans write down our algorithms in a way we can understand, and then a special program translates that into the raw ones and zeros that the CPU can actually fetch, decode, and execute. Okay, take a breath. So far, we've built one single, really powerful thinking machine. But the true power of modern computing, the thing that really defines our world today, is connecting them all together. Let's move to the final global layer of our blueprint. Think about it. For billions of computers all over the world to talk to each other without it being total chaos, they all need to agree on a shared language, a set of rules for the conversation. These rules are called network protocols, and they define everything from how to say hello to how to make sure the message you sent actually arrived in one piece. This is what makes the internet possible. The two most famous rules of conversation are TCP and UDP. Think of TCP like a reliable phone call. You dial, you connect, and you make sure every single word gets heard in the right order. UDP, well, that's more like sending a postcard. It's super fast. You just write it and send it, but there's no guarantee it'll get there. You use the right one for the right job. TCP for an important email, but maybe UDP for a fast-paced online game where speed is everything. And with all this data zipping around the globe, where does it all live? It lives in databases. You can think of a database as a gigantic, perfectly organized digital library. It's built to store, manage, and find unbelievable amounts of information in a flash. Everything from your social media feed to the entire global financial system. It all lives in a database. It is, quite literally, the world's memory. And there you have it. We did it. We started with a simple, abstract idea, true or false. That idea became a physical switch. Those switches built a thinking brain. We gave that brain instructions with software, and then we connected all of those brains together to create the incredible digital world that we all live in today. That is computer science. So after walking through this entire blueprint, from that first flicker of logic to this massive global network, it really begs the question, doesn't it? If this is the blueprint that got us here, what new layers, what new ideas are we writing into that blueprint right now that will define the world of tomorrow?